Okay, so in the previous class we saw some low power techniques where we saw gate level optimization techniques. In this class we are going to see architectural level, algorithmic level and RTL level optimization techniques. So if you see here, the first one is architectural level design parallel. It is known as parallelism. Okay, so if I have a single core out here, suppose it is working at 100 megahertz, the delay of the total delay is 10 nanosecond, and I'm giving an 5 volt and supply voltage, and say assuming that 16 milliwatt is the power which is required for this processor. Now instead of using a single processor, I use dual processor, where some task will be done here, some task will be done here, and finally it will be multiplexed here, right? And also, since I am using dual here, right, I am going to use half the frequency here, because finally I am going to multiplex out here, right? So the frequency given here, okay, for each of these modules, if you see it is in a frequency is in 100, here it is 50, here it is 50. So I have reduced the frequency. Also, since here 10 nanosecond is the delay, right? But here since I am going to finally multiplex it, I can afford double the delay out here, because they are working in parallel. So I am reduced, I am targeting 20 nanosecond delay, 20 nanosecond delay here, and that is why the power which I am going to use is only the power supply voltage. I have reduced it to half. So a reduction in power supply voltage increases the delay. Okay, but I can afford to have a larger double the delay, and hence I have decreased the power supply to 2.5 volt and 2.5 volt here. Now if I see the power equation, I have reduced the frequency by 2, and I have reduced the voltage also by 2. Okay, so it is square right here. So the total power, which was initially 16, now gets divided by 8, so it becomes 2 milliwatt and 2 milliwatt, and now these two together will have a 4 milliwatt of power, right? So that in this particular configuration, where I have a dual core, the total power is 4 milliwatt. Okay, finally the output is same, right? The same 10 nanosecond, the delay is same, the frequency is same. I am using 2 cores out here, right? So but the power is, if you see here, from 16 milliwatt it has come down to 4 milliwatt. So that is why if you see most of the modern processors, they have multiple cores. Okay, so the multiple core is not merely for increasing the speed. Okay, it also helps in reducing the power. Obviously, if I am going to use the same frequency out here, right, so the frequency output will increase out here, right? So but other way of looking at it is, if you use the lower frequency, you can reduce the power. So these are the some of the techniques. Okay, this is known as parallelism. So this is one method of reducing power. So if I now let pipelining also reduces power. Okay, now if you see here, this is one particular architecture where I am doing A plus B, C plus D together. A plus B plus C plus D is what is required here. So I have one adder module, and the delay out here is now 1 nanosecond. So I put some registers in between out here. So if I put a register out here, so here the total delay out here in this circuit is, once I put an input out here, the output will be available after 2 nanoseconds. So the throughput is 2 nanosecond, right? So whereas if I put a register out here, during the first clock, this output will be available here, and in the next clock this output will be available here. I am using an 1 gigahertz clock. Okay, now here also the total time taken for the output to come from here to here is 2 nanosecond, but the throughput is 1 nanosecond. Throughput means every 1 nanosecond I will get a new output, because I have placed one data out here during the first clock. Okay, the result of this addition is captured by this register. Okay, in the next clock this data can change. Okay, now this is going to compute in the next clock. So in fact, so I can keep the changing the data at a faster rate here, right? At every one gigahertz clock, I can change this data to a new data. So although the total delay is 2 nanosecond, the throughput is 1 nanosecond. That is, at every 1 nanosecond I can get one output out here, right? So if you find here, so if you look at the other way around, okay, if you are targeting only power consumption, then by using these registers, by using these registers, I can if I want to maintain the throughput as 2 nanoseconds, suppose here I am this design, if I use 1 gigahertz clock, I will get an throughput of 1 nanosecond, right? Instead of that, I am going to use an 2 gigahertz clock, right, and reduce the power supply of these two modules. Okay, in that case I will get an throughput of 2 nanosecond, right? So that will work exactly like this circuit. The speed will be the same, but since I am reducing the VDD, I will reduce the total power. Is that okay? Anurag, anybody? Right, this is one circuit, this is second circuit. One way of looking at, if I do pipelining, I'll be able to increase the throughput, right, by using registers in between. So I can increase the throughput. Or the other way of looking at this circuit is, if I want to keep the throughput same, okay, I am interested only a throughput of 2 nanoseconds, that is good enough for me. In that case, by inserting these registers, what we can do is, we can give a 2 gigahertz clock here, right? No, sorry, 500 megahertz, not 2 gigahertz, 500 megahertz. We can give a lower clock out here, so that the throughput is 2 nanosecond, which is good enough for us. But then we can reduce the VDD of these two circuits, because now we can afford to have a more delay in these circuits in this particular configuration. So that reduces the power. So that is one more technique to for a low design approach. Okay, so this we can do that. Is this okay with all of you? Okay. So this is like something known as retiming. Okay, these are all small techniques. Now if you see here in this particular circuit, so these two blocks are combined together out here, so there is an 8 nanosecond delay, right? So the clock will be accordingly. Now if you see here, right, in the same circuit, it's you have repositioned the register out here. Now it is on a 6 nanosecond only, so the clock frequency can increase out here, right? That is one way of looking at it. The other way of looking at it is, you keep the clock frequency same, because this was also working fine earlier. Okay, so now I have just reconfigured it. Now instead of increasing the clock, I reduce the VDD, okay, slightly. So now if you see here, in this particular configuration, the clock was such that it catered for 8 nanosecond delay. Here also, now I have brought this register here, right? So this is also 6 nanosecond, this is also 6 nanosecond, but the clock initially it was working fine, that circuit was working fine, even with an 8 nanosecond time period. Here I will maintain that 8 nanosecond time period. Okay, because if you see here, this particular there could be some other part of the circuit where there could be 8. So here I see that this particular block is just 6 nanosecond. So probably I can reduce the VDD and increase the time here, because I am keeping the time period of the clock, maintaining it as 8. So in that case, I can reduce the VDD of this block, okay, and these blocks as well, so that I can reduce the power. So these are the kind of things which are done in an implementation. And this is again retiming only. This is like you have a register here and you have register here, you have 4 gate delays. And now these registers have been positioned differently. Now it's only 2 gate delays. Okay, so you can all in these two circuits, rather than increasing the clock frequency, if you reduce the VDD, so you will achieve better power results. Okay, so that is the technique which is followed. Okay, and then you have something known as bus segmentation out here, right? Now for example, I think it is better explained out here in the next diagram. What is bus segmentation? Suppose in this particular I have 8 modules which is using an common bus. Okay, and now if you use a common bus, each of these drivers contribute towards some capacitance. So it will be a big capacitance out here, right? So this capacitance will be huge. Okay, now in this configuration, the bus has been divided into two. Okay, now these 4 blocks have been connected to this bus, and these 4 blocks are connected to this bus, and then you have a bus interface which will connect these bus on a requirement basis. Suppose most of the time, if you find that okay, these modules are communicating with each other, these are the modules which are communicating with each other, right? So you have to identify what are the modules which requires constant communication among themselves. So now if you compute like here, if you do this kind of bus segmentation, you will find this capacitance is almost now half of the capacitance out here, right? So the power consumption, so only once in a while when these 2 bus needs to be, some data requires to be transmitted from this bus to this bus or from this bus to this bus, so I can have a bus interface. Obviously this bus interface will not contribute this total capacitance out here onto this. Okay, so you can have some kind of drivers out here. So this is how the circuits in a micro in a PCB, when you have a motherboard and you have or within the processor also different modules. Okay, so it is not that all the module will communicate with every module always, right? It is most of the time many modules, they just communicate between themselves for certain specific functions, and other modules they specific. So you can group these modules depending on the functionality and assign a specific bus for them. Okay, rather than having a single data bus throughout your chip or throughout your motherboard. So this is known as bus segmentation. This is the techniques which is again generally very widely used. Okay, now if you see here, at the algorithmic level, you have a binary code and you have a gray code, right? So this you might have learnt in your digital design courses. So if you see here, the difference between a binary code and a gray code is, see, 0 is represented like this and 1 is represented in the gray code. If you see here, when you are moving from one bit to other in a sequential manner, only there is 1 bit change, right? So if you see this 1 is becoming 0, 0 is becoming 1 here, whereas here only this 0 to 1 there is a transition. Again, from coming from here to here, if you see here, from 3 to 4 here, right, all the 3 bits are changing in a binary code, whereas in the gray code at the same place, if you see here, there is only 1 change in the MSB, the LSB is remaining same, right? So so many a times we use counters and things like that. Suppose I want to introduce, I am taking sampling an input at every 1 millisecond, right, where the clock is in gigahertz. Okay, I have sampled an input. Now when to sample the next? After 1 millisecond. So what will I do? I'll energize a counter, load some value, high value, which is equivalent to say 1 millisecond, and then I will wait for that counter to come to 0, and once it has come to 0, again I will take the next input. Again I load this data in some new figure into the counter. Okay, and then I will wait for that counter to come to 0. So those kind of timing circuits, counters and things are there, which you can run in a binary code also. Now can I put gray code into that counter? Okay, why not? And if I put gray code, all that I have to see is that when the count is becoming 0. Okay, so in a binary counter, say for this counter, I will initially put 111 and I will keep decreasing counted. So after these many counts, it will come to 0. For a gray counter, I will put 100 initially, and this will also take 7 clock cycles to come to 0, right? So it will take the same time. But what is the advantage in having a gray code out here? If you see here, if I do this sequence out here, this is coming to be there are for this particular 0 to 1, 1 to 0, this is just an 2-bit counter it is shown, it has got a more number of transitions, whereas for gray code the total number of transitions is much lesser. It is just one transition per clock, whereas for a binary counter it is 1.5 transitions per clock. So because this actual data and actual sequence is not of relevance to us, okay, we are only wanting to run a counter to get 0 0 after a specific. So suppose I want only 6 counts, then I want the count, I want a timer to work for 5 counts. So in the binary counter I put 5 1 0 1, in a gray counter I'll put 1 1 1, and it will come to 0 after a certain time, right? So but then the number of transitions here, if you see here, is much lesser. So that is one way of reducing the power transmission. Okay, so these if you see any processors, there will be lot of counters for various activities. Okay, so I'm just giving one example. So in many places where the actual data doesn't really matter, it is just the count, where we can switch from binary to gray code. Okay, so this is one example which is given here. Now if you see the implementation of an binary counter, okay, you make an truth table and you find out the expression of A and B, and you have 2 flip-flops, right? So this is how now if you see, this is the gray code implementation. You will see hardware wise both these circuits are almost the same. So if you are implementing a counter, gray counter, instead of a binary counter, there is no actually additional penalty of hardware. If you see, it is exactly the same. Only thing is the way the outputs are connected out here is slightly different out here. Okay, this expression and this expression are slightly different. So if you find here, so the outputs are slightly different in both these two circuits. If you see the position of this NOT gate, so hardware wise they are exactly the same. So there is no additional penalty in using a gray counter. Okay, but the final switching, okay, is much lesser. Okay, so that is the advantage of using gray counter. This is another for a 3-bit. Okay, they have done the total number of computation, total number of toggles. From here to here there is one toggle. From here to here, if you see, there are 2 toggles out here. Here there is one toggle. Here there are all the 3 toggles are there. There is one. So in gray, obviously there is only one single. So average transition is 1. Here for a 3-bit, if you take the average transition per clock, it is coming out to be 1.75. This is now expanded to n-bit. Okay, so if you try to find out, and for an n-bit, these are the equations, and approximately you can see that for a large value of n, okay, the toggle of gray with respect to toggle of binary is 0.5. That means the power is almost half. The required power which will be there in a gray counter will be half, right? Because the activity cycle, it is we are targeting the activity cycle. So you can say the activity cycle of a gray counter is almost half of that of a binary. Okay, so this is one particular method of reducing the power. Okay, similarly in FM state encoding, right? So in digital design, again you might have done an FM state, right? When you these 1 1 0 0 and 0, this is one state, right? This 1 1 0 0 and 0 1, right? We assign these values, right? If there are 3 states, right? And so you require 2 flip-flops. And these arbitrarily we assign out of the 4 possible combinations. We assign 3 combinations, right? 1 1 0 0 0 1. That flexibility is available with the designer, right? Out of the 4, like this is a transition state diagram. I have 3 states, right? So I use 2 flip-flops. If I use 2 flip-flops, I can have 4 states. So among the 4 states, I can use any 3. So normally we just put some arbitrary 3 values out here, and then we go about designing the gates. Right now I am looking at saving power also, right? So now if I in this particular circuit, if I try to compute the switching activity, now if you see here, okay, So this is the probabilities now I have written out here, right? From 1 to 1, the probability is 6. From this state to this state, if it is going to move, the probability is going to be 0.4, right? So now here, if you see here 0.4, and from here to here the probability is 0.3. So the switching activity is here, if you see here, I have put 2 here because from 0 0 to 1 1 it's changing, so 2 and 0.3 and 0.4. okay, so this is the switching activity involved in this particular thing, right? And here, if you see here, it is a 0.1. So I am making an only, but there is only one transition which is happening from here to here, right? Now 0 0 to 0 1, only one. From similarly from here to here also it is 0.1, but it is 1 1 and 0 1. So I am writing only 1 into 0.1. So the total switching activity is 1.6. okay. So now initially I did an arbitrary assignment of these states 1 1 0 0 0 1, and now for a reduced power consumption, I am making these thing in a careful manner. okay, here since there is this change is higher, okay, so I am ensuring that there is no 2-bit change, only 1-bit change. So I am putting it 0 0 here and 0 1 here, right? Because in this particular path, if you see here, okay, the probability is higher, and that is why I am using only 1-bit change state here. Now if you try to compute the total, it is 0.3 and 0.4, and there is also from here to here also it is one more 0.1. So 1 into 0.1 0.1 from and then from here to suppose this is this 0.1 1 to 1, from here to here it is there are 2-bit changes, so that 0.1. So now it is the total activity out here is just 1 here, it is 1.6 out here. So you see, so now initially when we learnt about an FSM and all, and in those classes we never bothered about what to put here. Now since we are aware of the low power issues, now we can do a much better design, taking into consideration the power supply requirement also. okay, is this clear to all of you? Yeah, Bharat, Prerna? Yeah, okay. So this is some another technique which is known as bus encoding for lower power. okay, for example, this is my previous bit, okay, 0 0 0 0. The next bit is 1 1 1 0. okay, now if I am going to transmit this initially and this subsequently, so on the bus, okay, you will find all the 4 bit and 3 bits are changed out here, right? So so you will find there is a lot of activity which is happening on the bus. okay, now suppose I have some logic in which, okay, in case there is more than 50% change, instead of sending this, okay, 1 1 0 0, I will invert this and send this 0 0 0 1, right? If I invert it and send it, and now the at the receiver end again I invert it, okay, back again, so that I get back this. Now if you see here, when I am sending and inverting this bit and sending it, then I will find that, because you see the bit inverters and all, they don't consume that much of power, but the bus capacitance is very high. So we are trying to, because the bus it has got extensive routing, right? Within the, it could be within the chip, or it could be the outside chips to on a motherboard and chips communicating with each other. So we have to target minimum activity on these bus lines, because they are huge capacitances. okay, now what I am saying is, instead of sending 1 1 1 0, I am sending 0 0 0 1 here. So if you see here, I have inverted the data and I am sending it here, right? So you will find here there is only one transition, here there are 3 transitions. So what is the logic which I am going to apply here is, whenever the data is changing, if the change in data is greater than n, if there are total n bits, if the data is greater than n bits, I invert the data and send. okay, So the maximum number of flips which that can happen will be n by 2. Okay, if I send the data as it is, okay, there is a possibility that there could be n flips, right? If I have 0 0 0 0 and I have 1 1 1 1 to be transmitted, then the total number of flips could be 4, right? So that is, but if I am going to invert this data and send, so in that case the maximum number of data change will be n by 2, right? So is this graph understood by all of you? Right, what I am doing is before transmitting a data, I am checking it with the previous data, right? If the number of changes is more than n by 2, okay, what is n? The number of bits, okay, total number of bits. If it is more than n by 2, then I am inverting the entire data. So in that case there won't be those many number of changes. So the total maximum number of changes that can occur is n by 2. Okay, so in the receiving end I will again change that data back to. So if you see here, this is the schematic where how it is implemented, and this is the paper from where I picked up this data. Okay, now what is done here? If this is the input data out here, this is the polarity decision. Okay, so you have an data and you have the next data. You compare both those data, and if there is greater than, we will do the inversion of the bits during by change. No, the entire, now I let me explain that. I have a set of data here. Okay, I have a set of next data, so I am comparing both these data, and if there is more than n by 2 change of data, then I activate this XOR gate. So this XOR gate is connected to each of this data, so all the data will be inverted now. Okay, and it will be transmitted. And also in the bus there is one more bit which tells the receiver that I have inverted the data. Okay, and I am using again a set of XOR gates out here. So when obviously if I am inverting here, I get a one signal here, they get again inverted back. So the original data is retrieved back here. So if I go back here, if it is 0 0 0 here, right, and if I in the next bit, if it is 1 1 1 0, I have more than n by 2 changes out here, right? This is 4 bit, so more than 2 bit data is being changed out here. So instead of sending this data, I invert this data, so I send 0 0 0 1. Okay, so that is what is done in this particular circuit. Is it okay, Bharat? Okay, so this is known as bus encoding. Okay, essentially we are trying to change the bus data out here, right? Okay, so there is other technique also, which because of time constraint I will not cover. You can pre-charge this bus to VDD by 2 also. Okay, if you remember, we have discussed that particular concept in some other context in one of our previous classes, where we had the output charge to VDD by 2, and then from VDD by 2 it either goes to 1 or low. Okay, so those kind of techniques are also, but this is the one which mostly used, and that is the reason I have covered it here. Okay, now this is like an RTL path. What we do is, suppose this is an glitchy circuit. Glitchy means it has got high activity level, right? So instead of, if you have if this input from a mux has to go to a different mux, here if you see here, whatever activity is happening here is getting transmitted to this mux also, right? So if this is reordered, so here if you see here, glitchy is not actually glitchy, it means high activity level. Okay, so here if you see here, this activity doesn't affect this mux. Okay, so this is again reordering the RTL, and when we do an RTL design, so we need to be careful when we are having these muxes and control signals. So if you have a control signal which has got a large activity, then you might as well push it towards the end, okay, so that the preceding mux they don't get affected. So these are the kind of things which you have to be careful with, okay. Now in the memory, okay, when you see the 8086 memory, okay, this is just an example of 8086 memory. If I have an generally 8086, if you might remember from your microprocessors classes, that it has got an 1 mega memory, okay, but that is divided into two banks, okay, an odd bank and an even bank, and then I use the A0 bit to select either odd bank or even bank, okay. So this is like dividing the memory into two banks, okay. So what is the advantage is that the entire memory will not be powered always, okay. So whenever one data requires to be taken from the odd bank, this will be activated, and whenever even bank data requires to be taken, so depending on the LSB, only one of the banks will be activated at any point of time. Not both the banks will not be activated. So you have a lot of power savings, okay. So that is what memory. If you have a huge memory, you should try and have some kind of chip select logic function, where based on whatever address you have placed, based on that only that particular chip, that particular bank of memory is selected, okay. So that is done here. Here this is another memory partition technique. Here what they have done is, here this particular instructions which are accessed very frequently, okay, high activity level, they have put it in one bank, okay. Here some data which is not accessed regularly, okay, which is not critical, they have put it in a different bank. And here this is some moderate and switching activity, they have put in a different bank, okay. Now you will see that you can give full VDD to this bank, and you may not want to give full VDD here. Here you can give an VDD which is in between. So this is known as dynamic voltage scaling techniques, okay. So you will find that this memory is organized, okay, it's not a single chip, you have multiple chips based on the activity level. And those chips, if I go here now, if you say you have multiple memory chips, and the chip where you are accessing frequently, all that data should be put in one chip, so that these chips they remain idle most of the time, right. So the decoder should be able to trigger depending on the data address lines, should trigger only the power on off only that memory cell which is accessed regularly. So these remain off. Otherwise, if you see here, it is if it is a memory, there will be so many cells, and if you are going to give power supply completely to the entire memory bank, which is 1 GB, 2 GB, or whatever 16 GB, okay, there will be a lot of power wastage. So these kind of techniques are this known as memory partition technique, okay. So with that we come to an end of this class, so we'll stop it here, okay. Thanks a lot.